Heyo, who we all got in the chat right now? Good to see you there, Marley and Sam. I'm just messing with my chair. Good to see you there, Candido. And everybody is in the chat, getting some things loaded up right here. What should we do? What chapters do you want to review? You tell me. We start reviewing. Brady, good to see you there. Caitlin Raptar, good to see you there. What are we going to review? What are we going to do? Huge day, ladies and gentlemen. You got it. Chapter 14. Let's do some chapter 14 first. Chapter 14. Chapter 14, gonna do it here on Statue. Chapter 14. Okay, so when you get to chapter 14, let's put this in the notes, follow the video. Review 2. If you get to a chapter 14 question, trying to correct something over here also. So if you get to a chapter 14 question, what should you do? If you get to a chapter 14 question, what should you do? You get to a chapter 14 question. Correct me if I'm wrong. We can do some 320. We can do some 320. And Zoe, we could do some 479. Yep. We'll do some 479 and some 320. So we'll throw those in the mix. We'll throw those in. Maybe a good 15 minutes of those each. What do you need to do? You need to start writing the notation. Start writing the notation. And even Marley's saying right there, but choose between sample means and sample proportions. So if you take a look at what we have going on right here, I'm trying to do like 10 things at once. 10 things at once. What? Obviously roll into a ball and cry. No, Evan, don't roll into a ball and cry. You can see right here, we're going to grab the notation from our formula sheet. Now the problem is you have to know if you're doing a chapter 14 question. Chapter 14 is on the sampling distribution of the sample mean. So which line is chapter 14 on this? Chapter 14 is on the sampling distribution of the sample mean. So which line on the formula sheet is this? Sampling distribution of sample mean. So which line on the formula sheet is this? The sampling distribution of the sample mean. So it is going to be the bottom line right here. Let's go ahead and take a screenshot. Go over here and take a screenshot of this, drop it in a Word document, and start writing our hypothetical question. So the hypothetical question could be something like, Brian knows that the GPA of UT students is 3.7 with a standard deviation of 0.5. The distribution is skewed. Brian takes a sample of 25 students. Answer the following. 1. What is the mean of the distribution? So try answering this as I do this. 2. What is the standard deviation of the distribution? Is a sample mean of 4.0 an odd occurrence with, people are already answering. Canvas content, we could do some Canvas content too. Odd occurrence to C from a sample of 25. What is the shape of the distribution? Do we meet the conditions? This covers a lot of the chapters. So be very careful. The first thing you want to do right here is mark your what. So the very first thing you want to do is mark your what. So you want to mark your what to start. Mark your notation. Go. Doing 10 things at one time. So here we go with marking the notation. I'm gonna make sure, here we go, stat to review. I'm gonna mark this in the video. Of course, everyone's watching live, so does it even really matter? Because if you're not here, you don't know it. Okay, I've got my focus now. Okay, so this is chapter 14 review. Okay, so with this, what is this? What is this? What is this? What are those things in this problem? People might have it, and a lot of people are giving right answers in the chat. What are those things? A lot of people have already given answers. Start saying what these things are. You should know what they are in notation, full notation. If you scroll down to the formula sheet down below, you can get a lot more hints at it. Great job, Kaylin, right there. N is 25, says 25. So you look on your formula sheet and you're like, okay, I just found this. That is N is 25, so that's that. That is sigma is 0.5. So this is sigma, there's sigma. And mu, remember mu is mean. Now here's a mistake. Don't worry, Preston, we're throwing you some points here. Is there P for this problem? Is there P for this problem? Is there P for this problem? Is there P? So this is the same thing as that, technically. Is there P? Is there P? There is not. P is only for problems with categorical data for proportions. Did everyone hear that? P is only for categorical data when we have proportions. So this quantity right here, we can find a lot of the different things because we're going to know this quantity right here and this quantity. And what is one last bit of notation? And you can solve a lot of this now. What is one last bit of notation to solve this? How is there a mean if it's skewed? Courtney, really good question. We'll get into that. And Marley has pointed out y bar, which is said later in this problem. Y bar says is a sample mean, which is y bar, odd from a sample of 25. So you notice how we've gone through this and we've marked a lot on our formula sheet to help us see how to do this problem. And I think sometimes people jump into these problems. They say, oh, I'm going to do it, I'm going to do it. And then if you don't mark the notation, it's like, well, what am I doing? Well, the first question asks us, and we're going to go through this step by step now. What is the mean of the distribution? I'm going to answer Courtney's question too. What is the mean of the distribution? So the first question right here can be seen right there. So for question 1, mu y bar, which is the mean of the distribution, is equal to mu, which is equal to 3.7. Great job, because that's the expected mean of the distribution. This says expected, sure, I'm just going to hit a random help button. Help! The expected mean of the sampling distribution, that is equal to the true mean, which the true mean is this. The standard deviation, did anyone figure it out? I made it nice and easy. The standard deviation can be found by standard deviation of y bar is equal to the original standard deviation over the square root of n. So we take the original standard deviation of 0.5 over square root of 25, and I made a nice neat number. 0.5 divided by 5 is equal to 0.1. So there we go. That is it right there. It's not 0.5 though. The standard deviation of the sampling, so I maybe should have said, I probably should have said sampling distribution. So technically, I think our questions say this, I should have said sampling distribution. The sampling distribution is possible sample means of sample size 25. And remember, you've probably seen the central limit theorem a billion times from me now, but the central limit theorem applet shows this, that the central limit theorem states two things will happen as we take larger samples. 1, the distribution will become tighter. 2, more normal. So if you increase n here to 25, you will get a much more tighter and more normal. What will be the new mean of the distribution down below? The new mean for the distribution of sample means, great job Marley right there, will be a mean of what? What will be the new mean of the data below when I do samples of 25? What will be the new mean using the information above, because this is mu? So what will mu y bar be? This is the same concept again. Mu is 16, so what will mu y bar be? So mu is 16, what will mu y bar be? Mu is 16, so mu y bar will be 16. Well, it's not a sampling distribution for standard deviation. It's the standard deviation of the sampling distribution. So you can see if I increase the simulations, we start to get a mean, and it's approaching 16. More on that in a moment. But what will the new standard deviation be? If the original standard deviation was 5 with a sample size of 25, the new standard deviation when I continue the simulation will be what for this? With a standard deviation of 5 and a sample size of 25, the new standard deviation, and Candido said it, will be 1. Watch as I complete the simulation. It's 1. I had to use the law of large numbers to use more simulations. Why is it that? 5 divided by square root of 25 is 5, or 1. So 5 being sigma, original standard deviation, divided by square root of 25, and the simulation shows the same mean, but the standard deviation is smaller, hence tighter, and it is more normal. Once again, the two things the central limit theorem states. So very important to know this, that the standard deviation of the sampling distribution gets smaller, and that is the tighter part. I'm going to skip here to number 4, which kind of relates, or we'll do number 5, which I know I'm doing a little out of order. I wrote it. But number 5 says, what are the conditions? What are the 3 conditions? Starting with, what are the 3 conditions for the sampling distribution of the sample mean? What are the 3 conditions for the sampling distribution of the sample mean? What are the 3 conditions? Random, 10%, and then we pause. Now, QQ straight enough, no outliers, plot doesn't thicken, it's regression. Random, 10%, and large enough n. So once we do regression is QQ straight enough, no outliers, plot doesn't thicken. But then the conditions for these sampling distributions and beyond are random, less than 10% is sampled, and then also, and I'll show you right here, this is a different question we wrote, but random, does the problem indicate we randomly selected the observations? 10%, make sure to do lowercase n over capital N. Make sure to mark your notation and solve this. Find n if capital N exists. So we did this in office hours earlier. Then pause, put this pause in the chat, and then you have to figure out if it's success, failure, or large enough n. Large enough n is the one associated with means because we're dealing with quantitative data and the means of a quantitative distribution. Pause right there. Thank you, Noel. 1,000 points. And large enough n requires us to do the following. Does anyone remember how I described my original distribution? Brian described his original distribution in this problem as having what shape? Brian described his original distribution in the problem. It was skewed, right? So Brian said it was skewed. That means we need a sample size, great to see you, Tommy, also, of at least 25. So Brian's sample size, ironically in this problem, 25, is greater than or equal to 25. So do we pass the condition? Do we have a large enough sample size such that the distribution of the mean will be nearly normal? Do we? So once again, you look at the shape. The problem will tell you, or you'll see a shape. We do. And what does it mean that we pass conditions? By passing conditions, it means what? Like, here's an example where you fail the conditions. That's failing the conditions. Here's passing the conditions. The point to pass the conditions is to see if it's normal. I'm going to ask this again because you know we love some teaching to the test moments. Yes or no? I want you to click this in the chat and listen to me say it. Do you need to pass the conditions to calculate p hat and y bar, or either or? Do you need to pass conditions to calculate p hat and y bar? Yes or no? Do you need? Extremely skewed is 100 generally. Let's repeat it again. We pass conditions to see that the data is normal. So the answer, type it in capital letters. Do you need to pass, type it in the chat now. Do you need to pass conditions to calculate p hat or y bar? Do you need to pass conditions to calculate p hat, y bar? What do you think? You can type it in the chat. Do you need to pass conditions to calculate p hat, y bar? Might be on the test. Do you? Don't worry, we're throwing you 1,000 points. The answer is no. You only check conditions to see if it's normal. Let me ask you this. Brian spent $100 on video games last year. Probably more. Chelsea spent $200 on video games, and I approved. How much on average did Brian and Chelsea spend on video games? Brian spent 100, Chelsea spent 200. How much did they average on video games? Brian spent 100, Chelsea spent 200. How much did they average? 150. Did you check any conditions when doing that math? Did you think, I got to see if it's random, 10%, large enough n? You didn't. You just averaged it. That's how averages work. That's what y bar is. Let me ask you this. Brian and Chelsea own bunnies, but they're the only 2 people in their family who own bunnies out of 20 people. What is the sample proportion, 2 out of 20, for people in Brian's family who own bunnies? 2 out of 20 people own bunnies in Brian's families. What is the sample proportion of people in Brian's family who owns bunnies? 2 out of 20 people own bunnies. I want to create memories of you doing this. X over n. X is 2, n is 20. True, Helena. Yep, and we'll get into that here in a moment. 10% or 0.10% of people own bunnies. So in this example right here, you calculated p hat, and did you check conditions, yes or no? Did you check conditions, yes or no? Did you check any conditions to do that? You said, well, 2 out of 20 people own bunnies. No, you didn't. So to calculate p hat and y bar, there are no conditions. The conditions are used to see if the distribution is normal. Random 10%, large enough n for means, and random 10% success failure for proportions. So we're going to finish off this question. I'm going to mention about the 10% condition again. So please ask those questions too as we're going through this, because I'm going to try to hit a bunch of questions right here. So do we meet the conditions? Well, how about that 10% condition? Brian took a sample of 25 students. Explain to me, why are we not? Caitlin, good to see you right there. Last week's assignment, yeah, I might be able to. Might need to go over that more in person. Might need to. Plus, I don't know if I can show you the KUB data on YouTube. So good question, Caitlin. I might need to go over that. I might even make a dedicated video to that. That'd be a good idea, like a dedicated video. Thank you, Caitlin, for asking that. Because I don't know if I can show the KUB data on YouTube. I don't know if I have that kind of permission with it. I can show the wine data set. We did the wine data set earlier. So how do you check the 10% condition? So if you wanted to apply that proportion to a bigger population, that's what you would run into the 10% problem, kind of. And here's Marley's answer. So for the 10% condition, let's pin Marley's answer. Yes, because 10% of UT's population, well, when we look at this right here, take a look. Random means Brian randomly took UT students. So did Brian randomly select these students? Maybe. So as long as Brian randomly took the students. But Brian took 25. If you take 25 over how many UT students there are, is that less than 10%? The way to check the 10% is your sample size over the population size. Is that less than 10%? We can times it to a percentage, and it's 0.07%. That's not 7%. That's 0.07%. It's way less than 10%. Like 25 students is way less than 10% of all UT. And now the third condition is large enough n, which is the one I really focused on a moment ago. And since the data is skewed, we need at least 25. That's exactly how many I gave us for the problem. Going right here, 3. Is a sample mean of 4.0 odd? And I'm going to focus in just on 3 to make it clear what we're solving. So is a sample mean of 4.0 odd, yes or no? Are you talking about the bunny example? I like that. Is a sample mean of 4.0 odd? Yes or no? What do you think? It is. Layers, but it's... yeah, Evan, I can do that. I will do that, Evan. I'll do that in a little bit. Thank you, Evan. We will do that. Let me copy that, Evan. I'm going to put it in the notes to make sure I do it. And then you can definitely see it. So I've pinned that, Evan. And so Caitlin, if you're still here, we have a 320 question in the chat. And also, I think it was, I'm trying to remember who else was here, 479, Zoe, I think it was. Zoe, put your questions in the chat too, and I'll answer those. So Zoe, if you have questions, put them in the chat. And people are correct with the more than 3 standard deviations. So let's take a look at that. So question 3 says, is a sample mean of 4.0 odd? Well, that means sample mean of 4.0. Now, if you look, we have this equation right here. I'll zoom in on it. We can find the z-score for the sample mean, which is what this says, the z-score of the sample mean. So the z-score of a sample mean, to see if it's odd, is equal to the original sample mean minus the true mean over the standard deviation of y bar. And the standard deviation of y bar was found out to be a moment ago to be, we'll say equals 0.1. And then right here, we have mu was 3.7, and this is 4, and 4.0, and we get 3.3 over 0.1. Vinny, good to see you there. So this solves out to 0.3 over 0.1. So it is equal to 3, a z y bar equal to 3, which is just a measure of how odd the y bar is. So that's why we call it zy bar, versus the z p hat, which is a metric of how odd the z p hat is. So it is pretty odd. And the common mistake right here is to use the wrong standard deviation. A very common error, which you should not do, is to divide it by 0.5, which is not the new standard deviation. Make sure you're using the new standard deviation, which is 0.1. So 0.1 is the new standard deviation right there. So what is the shape of the distribution? I did kind of do these a little out of order. Since we meet all the conditions, which is the point of meeting the conditions, the distribution will be what? So you just have to repeat this. We're checking conditions to see if we can even do z-scores, because z-scores come from the what distribution, which we didn't meet it here. By meeting all the conditions, which we don't meet it here, Noah said it, it'll be normal. This is too skewed, but if you increase the sample size, it becomes more normal and tighter. So notice you could have even took the original standard deviation of 10.09. If you take 10.09 and divide by 5, i.e. square root of 25, you get the new standard deviation of 2.02 down here. And the simulation shows that the central limit theorem is a truth. You can actually obtain a normal distribution by doing the distribution of sample means. Should we do sample proportions? Then we might do Evan's question real quick. So we might take a small break from 201. But just do people want to review the sample? Studying 100 hours is well outside the bounds of the data we've collected. What is this an example of? That is extrapolation. Extrapolation. Helene, good question right there. So if you have, and I'll just show this real quickly right here. If you have data where people have studied like 0 to 20 hours for the test and you see grades are increasing and your friend says, dude, I studied 100 hours for the test. I should make like a 200 on the test. You would say you're whatting your model. You're whatting your model, which is when you leave the X bounds of your model. This is the X bounds. Repeat it again with me. We haven't said this word a lot lately. So what are you doing? You're extrapolating. I even like to put the X on it. Extrapolating. Extrapolating. Extrapolating can be done on the low or the high side. It is leaving the X bounds of your data, so you're making predictions where your model doesn't have data. Extrapolation is not a good idea. It has to be done for some things like time series to predict the future. Extrapolating roto wave, 5,000 points for a random roto wave. Man, are you still, I think you graduated, right? Now I'm sad. Making me all sniffly and sad because roto wave's not here. So I got like last sip of Monster Energy. Brian's powered by Monster Energy. Oh, not graduating in May, don't worry. Well, you better say hey to me, RotoWave. You better see me around campus and say, what's up, Brian? And I'll say, what's up? And then we'll walk on. Or you're like, hey, how you doing, Brian? We'll have more conversation. But RotoWave, hope to see you around campus. Man, all the way from 201, 320, and everything. Good stuff. Still working on it. Yeah, it's got like the last sip. You know how that last sip gets caught because of the way cans are? It's still got... All right. I've got tiny drops of Monster just fueling me. Let's do some chapter the goat Rodolfo. Exactly. Oh, it's awesome right there. I love the positivity with students. I think you should always try to give positive energy to those and others around you and fill up their tank on energy. I think it's a good thing to do. Okay, let's do some chapter 13. Chapter 13 is on, are we able to go through the question for corrections? There's no correcting the test. There's no correcting the test. Chapter 13 is sampling distribution of sample proportion. Now here's where people get stuck. People get stuck on these problems because they choose the wrong equations. So for these problems, when we solve it, what is mu? For these problems, when we solve them, what is mu? I'm being mean. For these problems, RotoWave's getting all the love and attention in the chat. I like it. For these problems, for the quizzes, oh yes, swing by. I will do corrections for people who come to office hours on my next one for the ones I missed. So Kelsey, swing by and we will do that. So swing by next week. I will be doing that. I will allow that because we usually do corrections during in-person office hours. So that way it's like you have to come in person and you meet with me and yeah. So so what is the mean for this? Like what is mu? You are right, mu is the mean. Mu is the mean, but here's the problem. When we do the sampling distribution of the sample proportion, thank you, Kelsey, good questions. This. Now there is, what usually confuses people is there is a mean for the distribution of sample proportion. So mu p hat, like I can insert a mu. So mu p hat is the mean for the distribution of the sample proportion. It's not truly, and I can't find my mu today. Where's mu bot at? Equation, insert. I know there's a mu on here. I'm just gonna grab a mu symbol. Wait, I turned my head and I saw it. There's mu. Mu p hat. Very important we put these things in properly. I not know you can do that right there. Mu p hat. Mu p hat equals p. How is this expressed to you in a question? I'm doing a bit of reverse teaching right now. How is mu p hat expressed to you in a question? You have to know your notation.
notation, brother.
Leo knows his notation. Old memes. How is mu p hat expressed to you in a question? How is mu p hat expressed to you in a question? How is mu p hat? It's a tougher question. Kind of. But how would I want you to write me something. I want you to write me a question almost. Like, how would, and this is where you have a higher level of learning, if you could write something that expresses a mu p hat. Kinda. I'm going to give it just a moment more and then I'm going to answer it. But can you express to me something that gives you a mu p hat? P hat is sample proportion, but mu p hat is the expected sample proportion. Give it 10 more seconds. Write me like a full question. Okay, here I go. Here's how it would be expressed. Here we go. Evan's on the right track. Well, so Marley, that would be, and so Marley, good answers. So Marley said 67 out of 100. What is the expected proportion? Correct. That expected from a sample. Expected from a sample. With this right here. So look at this. The company claims that 4% of their products are defective. Does everyone see this? So they're claiming a truth. What the company claims is P. So what mu P hat reads is if you took a what, you would expect to see what? Rotowave, you lost your points, did you? I reset points. Sorry. If you took a what, you would expect to see what? Uh-huh. I'll fix your points, Rotowave. Evan noticed their point. I'm sorry, I'd do that. Mubot gets mad at me. If you took a what? If you took a sample, you'd expect 4% of the sample to be defective. If you took a sample, you would expect 4% of the sample. Check your points again, Rotowave. If you took a sample, you'd expect 4% of the sample to be defective. So once again, read this. The expected sample proportion. Excuse me. The expected sample proportion. I'll wait till you see Rotowave's points. The expected sample proportion. Oh man, I might actually have to get some water. Or I might have to drink my Sprite. I'm actually going to open up the Sprite. I have no Sprite. 2 seconds. Water for the camera. Okay. Hence, I'll light off there. Just drink some sugar. Okay. So, if you took a sample, I do at home. I only drink water at home. When I get home, I either drink bottled water or I drink water in the morning. I'm bad with energy drinks. I go coffee, energy drinks, bottled water or canned water, then water. I know thanks for looking out for me. It's not too much to do. I gotta stop this monster habit, says Brian. Yeah. Make sure we put a space there, Braden. We'll have it happen. Okay. So the company claims that only 4% of the products are defective. So if you took a sample of things from the company, you would expect 4% defective. If 60% of students are in state and you talk to students, what percent would you expect to be in state? So answer this question. That's a good idea, Kelsey. I should do that. I think we have some emergency. This makes my day. We got a lot of the all-stars in here. Dee Dee, good to see you. If 60% of students are in state and you talk to students, what percent of students would you expect to be in state in your sample? You just go talk to students. 60% are in state. So what percent of your sample would you expect to be in state? 60% of students are in state. So if you talk to a bunch of students, you'd expect 60% to be in state. Does that make sense what mu p hat means? Be very careful. Which of these is it? Is it mu times p hat, or is it a phrase mu p hat? Is it the multiplication, or is it a phrase / concept of an expected sample proportion? It is the phrase. It is not mu times p hat. That's where people get confused. So wait, where's mu? But it's not mu times p hat. It's the phrase, the expected sample proportion, or the mean for the distribution of the sample proportion. It's a phrase. It's a phrase. We made it up. Mu p hat is for categorical data. Great job right there. You are correct. It is for categorical data only, meaning there is no mu. There is no population mean, but there is a mean for the distribution of the sample proportion. So the company claims that only 4% of the products are defective. You go out and take a sample of 500 and find that 30 are defective. Is this odd? 1, check conditions. We are a large company. Oh. Usually throw my trick. Yeah, this is good. I think this will work. Okay. What are the conditions? Condition 1. Condition 1, what? What is condition 1? Condition 1. Random. So the question should state in and of itself. I got hit on mute by moving. The question should state in and of itself random. Cue the random video. Rotowave knows. Condition 1, random. Condition 2, like you, Evan. I'm going to see it again now. Condition 2 is going to be less than 10%. I am COVID negative and no fever, but I either have a cold or a flu, hence I'm locking myself in my office a lot. But like I feel like 80.5%, I don't know. Feel right. Sorry to hear that, Rotowave. Do we meet the 10% condition, yes or no? Do we meet the 10% condition, yes or no? Click answer in the chat. This is a very clear yes or no with my invisible drink. Do we meet it? What equation do you need to check to see if we meet it? What equation do you check to see if we meet it? Thank you, DD. So Noah, go ahead and solve it. Preston, go ahead and solve it. You want to see if your sample size of n over population size. So you have to know your notation. You have to say the sample of 500 was taken, and we have a population size of hundreds of thousands, and that was Rotowave. So and then that'll be coming up here shortly. We'll do the success failure condition. And so we have way less than 10% right here. Way less than 10% has been sampled. I'm just hallucinating. That's the way it works. So we can even assume 100,000 and it's going to be like 0.05 or something. It's way less than 10%. So we have taken less than 10% of the population, which is what the 10% condition is. I call it 10% a lot of times for short. Less than 10%, thank you, of a population sampled. Now put them in the chat before we say the next condition. Put them in the chat before we say the next condition. What am I asking you to put in the chat? You know what you put in the chat. Before you say the next condition, you ask, is it categorical or is it quantitative? And you pause. So we pause and we think. Am I working with categorical or quantitative? Pause in the chat right there. Because when you have categorical data, I think we have back here today, we worked with categorical. You should have those pause right there. That's a pass, but we should have pause. Pause in the chat. It is going to be success failure for this one because it's categorical. So if you look right here, we pause. And since it's categorical, we ask ourselves, is it cat or quant? And this one would be cat. So it's success failure versus the other one we did today. We did a different one right here. So you'd go back here and you see we pause. And since it's quant, if we're dealing with quantitative, like this one dealt with a question about parking, how much people spend. Dogs in the chat also. The third condition is large enough n. Does everyone see the difference? You've got random, 10% every time, unless it's regression. And then the third condition is success failure if it's categorical, like we're doing a question right now on is something defective. That's categorical. A yes, no, is it defective? versus the third condition is large enough n if you are dealing with quantitative data where you're asking something like, how much do people spend on parking tickets, which is quantitative, an amount people spend on parking tickets. So we go back to our question, and what is the third condition after we paused? This is something defective? We're asking, is it defective? Is something defective? 4% are defective. So what's the third condition? And we have met all the conditions so far. Kind of pass fail. I call it success failure. Success failure condition. And do we pass it? And how do we check it? The math to check it every time, and please solve the math. Please do it. Don't be like, I don't know if I pass it. Let me just look. Solve the math. If you solve the math, you know the answer. So do we pass the success failure condition? I'm going to do another poll on yes, no on this. Do we pass the success failure condition, yes or no? And Marley's already been putting some of the answers in the chat. I'll start solving the math for you here. We need NP and Q greater than or equal to 10. And if you have these, N is going to be 500. So 500 times P. P is this. And then Q is equal to its complement, 0.96. So there we go right there. Whee! If we have at least 10 passes and at least 10 failures, correct. Good answers in the chat. So we need 4% of 500, which is 20, which means you can solve the other one because they must add up to 500. And there is NQ. So they're both greater than 10. So the answer is we passed. Everyone see this? Don't worry if you got it wrong. Just remember, we need to do NP and Q and see that they're both greater than 10, we pass. So what does this mean? Didi, we're pulling out the binomial distribution. What does this mean? By passing the conditions, it means what? Here's where you fail the conditions. Here's where you pass the conditions. What does it mean? Conditions failed, conditions passed. It's normal. It's normal. Why do we care about using normal distribution? We care about using normal because at the end of this, we are computing a what? Throughout many of these problems at the very end, we go in and we compute a what at the end, which, you know, you need to have the normal curve. I kind of let it pass. Garrett, good question right there. Brian said it's random. That's how it passes. Brian told you it's random. He said, I randomly selected these students. Z-scores are based on the normal. Good question, Garrett, right there. The question should explicitly state it. So you could have your qualms with this. Like, did they really take a random sample? The question should say it, especially on the test. And Z-scores are based on the normal. So we need to know it's normally distributed to calculate a Z-score. So you must have that. So let's go to the next two questions, and then we'll take a short break. We're going to do a little 320 after this. I have to go 330, essentially the code. Do you mind looking at it? I'll do some stuff here in Evan in a moment on it. So I'm going to, and I might not look at your code because I don't want to show too much code from a student, even with your permission, but lest everyone might do the same thing, but I'm going to talk about it. I might even try to weave in tool one. So if you're tool one, don't leave. I'm going to do like a 15, 20 minute section on 320 coming up here shortly. So next, say, what is the mean of the distribution? So we passed all the conditions. What is the mean of the distribution? What is the standard deviation of the sampling? Oh, Python code. That's some good stuff. Is what they saw odd with their sample. Okay, who has the mean for the distribution? Who has the mean for the distribution? Who has the mean for the distribution? What is the mean for the distribution? This is the easy one. Kind of. Good job, Tommy, right there. So the answer is mu p hat equals p equals 0.04. Does everyone see it right there? It's literally just this. The mean for the distribution of the sample mean is equal to that. What is the standard deviation of the distribution? Oh, I wanted to stay like that. So go ahead and solve. This one takes a moment, but I want you to solve it. So what is the standard deviation? I want you to take a moment to solve it. You got to do P times Q over N square root. Roll wave, you might have been in the class where I did that first, where P times Q over N square root. P times Q over N square root. I want to eat some pizza tonight. I want to start working out again. And then eat pizza. You were? It's like a year and a half ago now. I wonder if I was in Texas when I taught. It might be 0.018. That sounds about right. Let's check it. Okay, so standard deviation for the distribution of the sample proportion is going to be square root. It's quantity square root, 0.04. I'm going to write bigger. Sometimes I look at my handwriting, I'm like, I can barely read it. You can't read it. 0.04 times 0.96. That's Q. Please ask if you're stuck on anything. We got some hot dogs and sodium. I said that? Sure. 500. So it's P times Q over N square root. P times Q over N square root. We've also put in the chat. And it looks like 0.008. Is it 0.008? 0.008 or 0.009 rounded. 0.009. 0.009. Mebot's going crazy here. I'm going to ask, but do you do the square root last? Yeah, Marley, good question. So yeah, I'll show you in the calculator how it's done. It is P times Q over N and then square root of the whole thing. So P, I gotta check it, times Q over N, and then you square root the whole quantity. There you go. That's got it. Use this. Thank you, Nira right there. And please tell me, Nara, please tell me if I mispronounce anyone's name. Thank you so much for that in the chat right there. That is a reference, and that is a good reference. What I'm going to do with this to make this a little bit easier to remember is I'm going to go here and make it this. I'm cheating a little bit, but we're going to pretend it rounds to that. Rav, thank you, Rav. Okay, yeah, thank you. So with this right here, is it odd? Now watch this. When we draw the sampling distribution, what goes at the center? Well, the mean goes at the center, and the mean for the problem is 4%. So 4% goes here, and then this is 1%. So I rounded it. I wouldn't do that for the test, but look at this. And we could do the exact. Look at how beautiful this is. So what did we see in our sample? What was the p hat for our sample? Turned out to almost exactly 1%. The p hat in our sample was what? X equals 30. N equals 500. P hat equals what? And there's the answer to it right there. What does p hat equal? What does p hat equal? %. So we could do as a decimal. So that means we landed here. You know what's interesting? This question on the test could ask you, what is the probability of more than this? Because you should be able to figure it out using z-scores. What is the probability of more than 6%? 2.5 pressed and 5,000 points. Yeah. Empirical rule. So that's how we like to do test questions where you don't have to use the applet. So great. Thank you, Nicholas and Tommy right there. You got it. Why isn't p hat 4? So p hat is what we observe in a sample. We observed 30 defective out of 500. So p hat is what was observed in a sample. Sample proportion is when you take, like, imagine I say 60% of students are in state, you talk to 2, and one of them was in state. What is your sample proportion? So try that, listen again. 60% of students at UT are in state. You talked to 2 and one of them was in state. What is your sample proportion of in-state students? Marley, that is correct. And so 60% of UT students are in state. You talk to 2 students and one of them is in state. You are correct. The sample proportion was 50% or 0.50 as a proportion. But P equals 0.6. Can you scroll up? Yeah, standard deviation. I'll try to get it all on one screen. There you go right there. We rounded the standard deviation. If you want to go more exact, you could go right here and do P hat minus P over this. There's the exact z-score. So in truth, the exact z-score is a little bit over here, but then we'd have to move where the 6 is at. So if we were to erase this right here and only use z-scores, if you carry all the decimals, this is the carry the decimal version, which we didn't really do. We cheated with the decimals. if you use z-scores, it turns out to this. Does that make sense? Who follows me that if you were to divide by the actual standard deviation, then you get a z-score of 2.2, and I'll write the math down below. So we did a nicer version. It would be p hat minus p over standard deviation of p hat, which is equal to what we saw in the sample minus the truth over 0.0087, and that is equal to 2.24 or something like that. Does that make sense? So that's if you carry all the decimals, 2.28. If you carry all the decimals, you get this right here, which is going to have less than 2.5. So this would be less than 2.5%. It's going to be like 2% or 1.8% or something. We don't have used the applets on the test, so we wouldn't ask you to get exact numbers. Okay, we did that's chapter 13 with the conditions, and that's using all the equations. And so Marley, P is the truth, like 60% of students are in state. It has nothing to do with the sample size taken. And then P hat means you took a sample and observed in that sample a proportion. Like 2 out of 10 people own bunnies, that would be a P hat because you're saying that 10 people is what you sampled, and 2 is X in that instance, which is number of successes. Is this making sense, Marley? P hat is a sample proportion which is observed, and good to see there, Harish. And P hat is the sample proportion observed, and P is the true proportion. Test got another mummy. How do we get 0.01? P times Q over N square root. P times Q over N square root. And then we cheated on the rounding. Don't change your rounding. It just made the problem easy to show the example with. It was 0.087. And then we rounded it up. P times Q over N square root. P is 0.04. Q is its complement, 0.96. And there we go. So Evan's got a really good question, but is related that we selected 3 variables, 1 cat, and the first interaction plot, and then we get again to select the 3 new variables. So wait, Evan, can you expand? I'm gonna do a little. So here's the thing: if you think this doesn't apply to you, it does. I'm gonna try to weave in some 201 into 320. So, and I might even, if we have a 479 question from Zoe or anyone, I'm gonna try to weave in those questions into this all. So this is BAS 320 regression review, and regression is something on our test. So what we're doing in 320 right now is we're doing multiple regression, which just means multiple X's. And here, I'll show you some of these models. Here we go, what you're gonna see. So don't worry, this will relate to 201. So if you're 201, I'm gonna try to make this as 201 important as possible. I'm pulling up some data from students from 2010. Soon they'll be as old as your parents. I'm old. And then we're gonna go right here. We're gonna create a model predicting somebody's weight from their height and their gender, but the interaction between height and gender, P times Q or N square root. That is correct. That is the standard deviation. So what we have right here is a model predicting somebody's height, or their weight, excuse me, from their height and their gender. Now take a look, and 201 or 320 can answer this. Which of these lines has a greater slope? The male's line or the female line? Which of these lines has a greater slope? The male line or the female line? Which of these lines has a greater slope? The male line or the female line? The male line has a greater slope. And what this means is males who are taller generally have a higher weight than we would like. For 2 males who are otherwise identical, but they differ in their height by 1 inch, the male is probably going to weigh a lot more than a female would, who differs than another female by 1 inch. There's a stronger slope to the male line. And this is what we call indicator variables, not on your test. And you can see it in the output. Now remember, you've already seen where there's an intercept and an X. In 201, your output looks like this. But here's tall males equals higher weight. Usually generally associated, if a male's taller, they generally weigh more. That's kind of what we see. But think about this. Let me ask you here, how would you interpret R squared? How would you interpret R squared? Remember what R squared is? This is practice for your test in 201, which is a thing you can also put in your 320 assignments. How do you interpret R squared? This time there's multiple X's. Pretty much, Ralph. Like when you get to the test, it says interpret R squared. That's why I'm trying to make this 201 friendly right here. What will you write? Now, this is something you wouldn't see because it's a multiple regression, i.e. multiple X's. So what would you write? So you have to do blank percent of the variation in y. Preston, you got it, but make sure it's filled in. It's got to have all the variables in it. You got to be blank percent of the variation in y is explained by the variation, and now we have the x's, which is not 201. So be careful, you'll just have one x in 201. Blank percent of the variation in y is explained by the variation in x's. Anyone want to take a guess at this? We'll throw some points. I'll give it more. 42% of the variation in weight. Close, Caden, and we'll throw you the points. So Caden, for 201, where we just make the simple model, we call it simple because it just has one x, one y. Caden, you're 100% right, and you would just change this to 36.13. Now, I am doing a little bit. I'm putting in here for 320, some advanced stuff, because we're making a video for them too right now. This would be, you're very close, 42.37% of the variation in weight can be explained by the variation in height, and accounting for the interaction between gender, male and female. Or you can just say, Elizabeth, 42.37% of the variation in weight is explained by the regression model. The x's, they make the regression model, which is making these models of lines. So you just usually sometimes say the x's or the model. You might just, or you could say the x's, which encompass height and gender and their interaction. So don't worry, in your world, you'll just say the x, because in our world right now, we just have one x called simple regression. And now this is called multiple regression when you have multiple x's. So here's the thing though, you can still have residuals. And this is what 320 should be doing. What people ask in 201 a lot of times is, how do I know if something is a big outlier? Well, there's one big outlier I'd say right here. Does anyone see that big old outlier? Where's that big old outlier? Do I see it here? Where's it at? I have to plot another way. There's a big old outlier. There's a few. Where's that outlier? Do you see it? Bingo. It has a huge residual. That means, so we'll zoom in right here, and here's a residual plot. Doing the check regression code right here, we can see a huge low outlier and also some extreme high outliers. What does that mean? These people were predicting weight weigh about 148 more than they were predicted to weigh. This person weighs about 100 and maybe 25 less than they were predicted to weigh. What's really great is when we look at the summary output, it actually tells us what the lowest residual is. When you look at it right here, notice this residual of negative 121 is this point. The residuals of 145 would be this point right there. That's the most extreme residuals. And the most extreme residuals are going to be the points that are outliers that are far away from the model. It might be that one right there. I don't see the low one. Sometimes the graphic doesn't show all the points, but the outliers are far away from the model. So I would say there's some outliers. Here's another thing we look at also. Why do we look at a residual plot? This is something you have to know for 201, and we're doing like how 320 would do it. But why do you need to look at a residual plot? QQ straight enough, no outliers. What's the last one? Look at a residual plot to make sure what? Plot doesn't thicken. And I would say for the most part, do you think I think it passes or fails? That's how I would draw on it. Do you think it passes or fails? And I'll show you some crazy ones here in a moment. What do you think I'm trying to say to you? I think it passes. Yeah, if you notice, they're about the same. So I think that's, yeah, I think it passes. It's not really bad, and I bet you the p-value is pretty bad. I would say it passes. But now, let me show you some data which has major problems. So I need the EX3 abalone data. Okay. And let me attach it. And EX3 abalone. And elam, it's meat weight, meat.weight, length, just length, sure. And visualize model. How many conditions do we fail? QQ straight enough, no outliers, plot doesn't thicken. Maybe you'd like to see a residual plot on this. Maybe you'd like to see a residual plot. How many conditions do we fail? Woo-wee! That is failing a condition. How many conditions do we fail? How many conditions do we fail? QQ. Outliers probably fail. Outliers, funny enough, I do agree, but outliers are probably the least of our concerns. Here's your outliers. Not all four, though, because to do regression, you have to have quantitative data. So to even make a scatter plot, both variables have to be quantitative, and I took the weight of something and the length of something, which is two quantities. So to make a scatter plot, you have to have QQ. So you can also look at residual plots for straight enough. It does look parabolic. Exactly. And I'll show you a cool way to fix this in a second right here with transformations. So the straight enough, this is the line itself. Is that a good way to model this data? Is that line going through the data? No. As Didi said right there, we should use some sort of parabolic or some other relationship. So it is definitely not a straight enough relationship. Who notices when I say plot thickening what we're talking about? Plot thickening is when the plot gets thicker, known as heteroscedasticity. Compared this to the previous one I drew, where it had about the same thickness. It looks about right. But this one is heteroscedastic. What's really cool, and this is real data from a creature known as an abalone. They look actually really crazy. People get their meat. I think it's a delicacy now. But people take these abalone creatures and eat these abalones. So there's abalones, but it's like a sea urchin type creature. Abalones, just sure. There's abalones. It's a real food people eat. Yeah, seafood. That's the way it goes. And so what we can do is we can do what's called fine transformations, and this will run a vector of transformations. This is not into a one. Fine transformations, and here you go. And it creates it a lot more linear, and the R squared is increased, meaning we've explained a lot more of the variation. And it fixes, here's the highest R squared. We still have a little problem of heteroscedastic towards the end, but it creates a linear relationship and we can run the transform model. All but QQ, correct, Marley, right there. So, and look right here, the R squared is much higher, which means we went from explaining very little of the variation. I don't know if I ran the summary on it. Let me look at the summary. Right now we explain 78% of the variation, and then with a transformation, we go up to 95% of the variation. Well, there it is right there. So you fix some of the issues, doesn't fix everything, and that's a story for another day. I'm gonna look at one more thing in this day, then we're gonna go back to a one. We might do some probability next. Let me look at the abalone data and see if I have in here. I don't have a categorical variable. So I'm gonna do a wine data set with the SIR assignment. No! Okay, we'll do one more thing right here, then we're doing more 201, so stay tuned. Okay, so this is another model where I'm predicting the height of an individual based on their handedness, and also their GPA. So what did I didn't do data equals. Okay, there we go. No, what'd I do? Oh, it's too large. There we go. Whoa! No way. What? It's significant? That's crazy. That is crazy. So what we actually have to do now is we have to run a drop one test on this, which 201, sorry, this really doesn't apply to you. Is the impact of handedness significant? And the answer is yes, which I have no idea why. This is probably just a type 1 error. So right here, you can see the lines have different slopes, which is the kind of the impact of the interaction. To where when we have weaker interactions, like if I try to find a weaker interaction, then we'd have like weight right here, and that's weaker, and then the p-value is higher. So p-values just tell us what? Now this is 201. P-values only tell us if something is, think SS, p-values only tell us if something is what? P-values only tell us if something is what? This is what we should know in 201. When a p-value is less than 0.05, it indicates that what we have found is statistically significant. So when doing interactions, which is a 320 idea, so we're going to go back to a 100% rotowave, good seeing you. So if the lines look like this, there is no interaction. If the lines look like this, there's a stronger interaction where the way in which we have the relationship described would depend on different levels. So this indicates an interaction, i.e. statistically significant, unlikely by random chance to see those differences. So this is something 320 has to know, that when they're seeing a statistically significant interaction, the lines will be not what, or more what. No, Ralph,
My goat too.
Lines will be more what when we see statistically significant interactions? The lines will be more what? The more, because if you go back, what I did right here, I have a not as significant interaction behind me, and then I have a more significant interaction, i.e. lower p-value for this one, higher p-value for this one. This is less significant. More likely by random chance to see what we're seeing here. So the answer is when it's more significant, the lines are more perpendicular, or they go in different directions. When it's not significant, the lines are more parallel. So not significant, more parallel, significant, more perpendicular. Not on your 201 test. Should we do some probability? How about time for probability? I think that was about a 15, 20-minute section right here on this. So what should we do? That was only 13 minutes. No! Should we do probability? Thoughts? Anything? Bueller? Garrett says yes. Okay, Garrett, let's do it. Okay. So one thing I want to stress to people is this. You have to know the definition of independent, mutually exclusive, and you have to know what disjoint means. What is the good news on knowing these definitions? What is the good news on knowing these definitions? Like, there's something easier about this. I'm going to write some things right here. I think this will work. So I'm trying to come up with another one. Let me think here. Oh, wait. Let's say Brian. Okay, bring it up there. Legally. Okay. Someone's going to outthink my question if I don't put all those things. So it might be. These mean the same thing. These mean the same thing. And if you are watching our class right here, or watching the online office hours for the first time, feel free to attend more of these. I'll just answer questions. You come in here. We usually do work. We usually do assignments. I'm going to ask you the question we've been asking every single time. What are you going to look at before I ask this question? Before I give you this, you're going to look at the what? I wish everyone would get this right when they get to the test. The formula sheet. You're like, Brian, I've done this a billion times. Well, I'm reinforcing the behavior. Okay. So you're getting a question and you need to have the formula sheet open. Before answering this, go to the formula sheet. Go to the formula sheet. So you need to go to the formula sheet right here. Before answering this, you go to the formula sheet. And you go right here. You go down to formula sheet. You look at the formula sheet. And what do you see? I hope we get more right answers than wrong answers these days. Don't worry if you got this wrong. But the thing is, go to the formula sheet. We got one of our best percentages here yet. So if you see right here, it says right here, multiplication, things are independent. We use the words A and B. You've probably said this and I forgot it. Can we write out the formula sheet? Yep. You just can't have other things printed on it. Yep. Can be written out or printed. You can't have other things on it. No notes are allowed on the test. So with this right here, to multiply two events, they must be independent. And now we need some good definitions of what independent means. You're welcome, Kaden. Good questions. So independent means, the way to test it is the following. The test is, A happens. Well, one thing happens. This influences the other thing. I'm going to decrease font a little bit here. That would be independent. Let me make hers. This does not influence the other. Independent. I want you to be asking yourself these questions as you do each of these. And this would be one thing happens, the other thing cannot happen. That's mutually exclusive / disjoint. The other thing can happen. And that would be not mutually exclusive / not disjoint. Okay. So here we are. So for the first one, you're welcome. Good to see you there. Appreciate it. So with the first one right here, let's talk about A and B. So answer in the chat, are these independent, dependent? So you need to give me independent or dependent, because it can't be both. Those are mutually exclusive. And you need to tell me disjoint or not disjoint. So you're going to answer for A and B, and then we'll talk about it. So answer both. Answer both, like answer in one thing. Answer both of them, though. Because it's two separate ideas. Like, it's two separate ideas. Because you can have independent disjoint, dependent disjoint, independent not disjoint, dependent not disjoint. Actually, I think one of those you can't have. Because if they're disjoint, they're dependent. So you can't have disjoint independent. That's the only one you can't have. Oh. So remember what I just said? Don't worry. You can't have disjoint independent. That's the only one. That's the only combo I think you can't have. So let's look. Let's ask the first question. If Brian is 42, which he is, does that influence the probability of Brian being a teenager? If Brian is 42, does that influence the probability of you thinking Brian is a teenager? If Brian is 42, does that influence the probability? Yes. Meaning for this first example, they are super duper what? Exactly. And Preston said the probability goes to 0 because you can't be 42 and a teenager. That's what they tell me. I say I'm a teenager. I'm wearing a Nightwing shirt. That's what they tell me. I can't be a teenager. Teenagers scared of me. MCR was right. Then the fact that you can't be 42 and a teenager means what? The fact that if you're 42, you can't also be a teenager, it means what? The fact that if you're 42, you can't be a teenager, Rav got it, means they're disjoint. So the answer to the first one here, just remember how we check these, is if Brian is 42, well, then I know he's not a teenager. Now, that does actually mean disjoint too, because it means the probability went to 0, but it also means dependent. So all disjoint things, by virtue, if you know disjoint, it does mean dependent. But be careful, if you know dependent, it doesn't mean disjoint. We talked about some of those earlier today. We might have one of these here. Let's do B and C. You know this dude, Brian, is a teenager. Is he drinking coffee? Don't go too esoteric on this. You know Brian is a teenager. Is he drinking coffee? Don't go too crazy. Rob's going where I'm going. I'd go independent. Because knowing Brian is a teenager, which I was drinking coffee as a teenager, put a lot more sugar in it. So knowing Brian as a teenager would not really tell you anything about whether or not he's drinking coffee. Unless you go like, well, teenagers drink coffee less or more. Wait a minute. No, we won't go too extreme on it. How about, is it disjoint or not disjoint? Can Brian be a teenager? Can he be drinking coffee? Can Brian be a teenager? Can he be drinking coffee? And what does that mean? Not disjoint. Because Brian can be a teenager and he can be drinking. It can happen at the same time. Like, oh, a teenager's drinking coffee. Whoa, a not disjoint event. That's what I say every day. So now we go and we do, let's do this one down below here. Sure, let's do C and D rather. Okay. Well, it's kind of the same. I'm trying to think if I put other examples in here. Brian is drinking coffee. Brian can legally buy beer in Tennessee. So is that independent or dependent? You know Brian is drinking coffee. Do you know Brian can legally buy beer in Tennessee? Independent or dependent? Yep, I think Noah's got it. It's independent because knowing I'm drinking coffee would tell you nothing if I can buy beer. And then it's not disjoint because I can drink coffee and I could legally buy beer. So does that make sense? This is how you check them. Does everyone see these checks over here are the key things to know? So you have to know how to check independent, and I would walk through this in my head, and you have to know how to check mutually exclusive disjoint and just walk through it. So they're different questions. Independent means if one thing happens, it changes or influences the probability of another. Probably my favorite example of independent would be something like, we'll put E and D right here. It is snowing, and it's below 32 degrees. So with E and F now, what are E and F? E and F are what? So we'll highlight what it is. I think so, Noel. What are E and F? They are dependent, but are they mutually exclusive? So dependent means if it's snowing, is it more likely or less likely to be below 32 degrees? They are dependent because snow would depend on the temperature. And then you have to ask for the next one, could it be snowing and could it be below 32 degrees? So in this example, I'm going to change it in 1 second. This is dependent and this is not disjoint. But let's say it's above 100 degrees. So now what is the example? Notice how I can make a small switch, which gives you a different thing. Let's say you know it's above 100 degrees today. Does that influence what you think about snowing? And then what did I just tell you by having you think through that? If you know, good job, Rob, right there. So if it's above 100 degrees, does that influence what you think about snow? If it's above 100 degrees, does that influence what you think about snow? Great job, Noah, right there. It's dependent because if it's above 100 degrees, you know it's not snowing. And then it's disjoint because it can't be above 100 degrees and snowing unless we're in some bizarre world where that's possible. Like, I don't know, it's like snow's like negative, absolute zero snow falling down, hitting the earth and just melting on impact. I don't think that happens. Not likely. So with this right here, I hope this is good practice because when you get to these on the exam, there's questions just like this. You need to stop and ask yourself, does this influence what I think about this? It does. It's dependent. If this happens, can this other thing happen? Yes. It's not mutually exclusive. You have to follow these steps right here and just think through each one and give yourself the tests. Let's do an at least one problem, or if people have new questions, I'm just throwing out ideas because I know what people get stuck on. I'm going to give you a harder version of at least one problem, which maybe mimics the test because I love mimicking what the test looks like. So at least one problem, test review, or all test review. Okay. Brian has spent all his money on lottery tickets. Don't be like Brian. Make a full sample space showing what will happen on Brian's only two lottery tickets. The lottery tickets have a probability of winning of 10%. Okay. This is like the car question, which is a good one to practice. And once again, I mimic things that I remember on the test. So when you think about those, what is the probability Brian wins on a lottery ticket? I mean, it gives it in the question. And play the lottery responsibly because a lot of people lose money. That's how a lottery works. What is... So what I always do for these problems is I write everything out. I was so bad at this in school, I never wrote it out, but I promise you, writing it out makes more sense. You see it. Has anyone seen me solve a problem? You're like, that's so easy. And then you're like, wait, why is it easy? Because I write it all out. I'm talking to past me. Like, I'd be like, Brian, this is you from the future. Start writing out your work and tracking what you're doing. I don't know. Probably won't go back. So we have the event and the probability of said event. Two events, you win or you lose, as in don't win. Probability of winning is associated with 10% and losing is 90%. So you either win or do not win the lottery. We'll define that as lose. Now here's the thing, we're buying 2 lottery tickets. Can you give me the sample space of what can occur? Can you give me the sample space of what can occur? Write for me in the chat the sample space of what can occur with 2 lottery tickets with winning and losing, with the permutations of winning and losing, as in respect to order. Correct, it's win or lose, but that's for 1. And Noel, great job. Noah and Noel, good attempts and good jobs. And Preston, we are going to do respect to order right there. So we are going to do win-win, win-lose, lose-win, lose-lose. And that is the sample space, which is defined as everything that can occur. So here's the thing. When you buy a lottery ticket, and you got that lottery ticket in your hand, what do you think that lottery ticket thinks about your other lottery ticket? Here's my 2 lottery tickets. They might not look like lottery tickets, but they are. This lottery ticket is completely what of this lottery ticket winning? This lottery ticket here is completely what of this lottery ticket? Because it don't care. I don't care about this lottery ticket. Independent. Independent. One lottery ticket winning is completely independent, as The Rock would say. It doesn't matter if you win on one lottery ticket. It's not going to influence the probability of another lottery ticket winning. So what we can do is we can take the win-win and say you win and then you win, or you win and then you lose and then you win, you lose and then you lose. So this is everything that could occur from 2 lottery tickets, because you're either going to win-win, win-lose, lose-win, lose-lose. So what would be the probabilities for these? So what would be the associated probabilities over here? So these are the events with 2 lottery tickets. So what's the probability you win on both lottery tickets? What's the probability you win on both your lottery tickets? What's the probability you win on both your lottery tickets? Ah, great job, Rob, right there. So we'll do that. We'll write math right here. Math, and then answer. It's 0.1 times 0.1, so it's 0.01. What's the probability you lose and then lose, which is the most likely occurrence? What's the probability you lose and you lose? I've been playing Diablo 4, as people probably heard, and it'll be like your glyph has a 70% chance of working, and then I'll lose on all 3, and I'll be like, that's not likely! Like 30% roll 4 times in a row, like 0.3. I hit a 0.3 to the 4th power. I'm like, I think this game is rigged. So, of course, I only start noticing when I lose, and I do play too much. Lose and... Oh, this is the math section. Leave it to Brian to be playing a video game and be like doing probability calculations about the game, talking about the fairness of the game. What is the probability you lose and then you win? What's the probability you lose and then you win? I'll start writing the math right here. What's the probability you lose and then you win? You lose and then you win. Well, there's the answer. 0.09. Yep. Chelsea says to Brian, she doesn't want to be rich. She only wants him to win once. This is a tougher... maybe we won't do that first. Oh, yeah, just pretend I didn't say that question. What is the probability Brian wins something? It's pretty... If you write out this table, you can actually figure pretty quickly the probability Brian wins something. What is the probability Brian wins something? Which can be found by doing 1 minus all losers. 19%, yep. Also, you can just look at the table now that you made and add up these values. And you can also see why it's a 1 minus. Because, great job, Noah, right there. Yep, and then that's it. That's the math right there, because you notice we just plug in the probability of all losers. And that would be this. And there's the probability down there associated with that. So if you plug in all losers, everything but all losers, 1 minus, you get the probability. What is the probability of Brian winning exactly once? What is the probability of Brian winning exactly once? Which I swear maybe a test question kind of asked that. Just trying to drop some hints that if you draw it out and get to a tough test question, you're like, I can solve this. Brian showed me some steps. What is the probability you win exactly once? I think Preston has it. Squeak, squeak. Oh my gosh, I hope you guys can't hear that. Oh. Just bad. 0.18, 0.18, 0.18. W Preston right there. Good work. And so this question right here, we don't usually give you big, complicated ones if we do like a one-off question. Definitely heard that. I'm sorry, TT, right there. I heard it too. It started doing that. I might complain to XPen. Oh, I'm mad. Your board squeaks. It's a nice tablet other than that. It's a beautiful tablet. How about this? Let's do a tougher version. Brian is making it big. Chalkboard is worse. True facts right there. Brian is buying tons more lottery tickets. He now has bought 20 lottery tickets. They have a bigger jackpot. Jackpot? Jackpot. I don't even know my jacket. A bigger jackpot of millions or $10,000. This is just superfluous information. The probability of winning is only 2%. What is the probability Brian wins something? Let me mute myself and ask my phone. What is 1 minus 0.98 to the 20th power?
That would be approximately 0.3323.
So what's the answer? Who knows? Oh, you heard me? Oh, did I do the voice? No, I meant to hit mute. Candido, I didn't hit the mute. I think I meant to hit mute. Oh no, Preston, did you hear it? Either Preston solved it or heard it. We'll show how to solve that. Okay. So thank you, Candido. Oh, I didn't want you to hear the answer. I actually didn't know. It's not one of those fake oops moments. Okay. So if you've worked through many of these problems with us right here on at least one problem, first thing you always do is write your probability table. Writing the great job, Noel, right there. Perfect answers. The probability table is where we take the event, the probability of the event, and then we write right here, you either win or lose, and the win is this, and the lose is this. This is a proper sample space. All probabilities are between 0 and 1, and the sample space has a total probability of 1, which is the sum of the probabilities in the sample space, because they're all disjoint, meaning you either win or lose. They can't both happen. And they are dependent. Winning depends on losing. With that, we are going to say now our sentence. This is where people get stuck on it, and you can tell a lot of people in the chat are really good at this because they've been doing this multiple times. What are the two things that could occur? Remember, Brian wants to know winning something. So win something or what? You either win something or what? And if you can write this sentence right here, you get it down. You either win something or what? What do you mean, Preston? You're on the right track. All losers. So you either win something or you lose on every one of them. You buy 20 lottery tickets. Either all 20 are losers or you have at least one winner. Now, one of those things must occur, so it has a probability of 1 when you think about probabilities. Now we change the or to addition, because when we say or, we're talking addition. These are disjoint because you can't win and lose. And then we figure out the probability of all losers, which we can subtract from the probability of 1 to find the probability of win something. We just algebra it over to the other side. So the probability of all losers is you lose on the first, you lose on the second, you lose on the third, you lose on the fourth, you lose on the fifth, and the sixth, and seventh, and 20th ticket. Why am I able to multiply the lottery tickets together when I say the probability of losing and losing and losing? Because each lottery ticket is what of each other. I am able to multiply the probability of losing and losing and losing and losing because they're all independent. The previous lottery ticket doesn't care about the next one.
It doesn't matter.
Doesn't matter. So they are all independent. So this right here achieves a probability of about 33%. 33%. If you have a 2% chance of winning and you buy 20 lottery tickets, you have about a 33% probability of winning something. And that's how we solve at least one problem. Just remember your steps right here. It really boils down to practicing these by doing the steps. I'll have a lot of different steps for a lot of problems. I know it's a lot to remember, but sit down, write down a problem, make up your own, try doing the steps, even ChatGPT, ask it to make up some problems for you. And then if you think about, this is what I beg of you, is when you're doing problems, create steps. You know there might be at least one problem on the test. Which still true for the Powerball. Powerball has a much lower probability. And so there is a way of doing it with Powerball. Like, what's the probability? See, watch this. I'll show you some craziness and then we'll do another question. Okay, so here's ChatGPT. And then create a graphic that shows the probability of winning at least one time with the Powerball, where someone is buying enough tickets. Oh my gosh. Let's see what it does. There's the probability. That's pretty crazy. So you can actually do it right here, and it's probably gonna do a lot of the same calculations. Yeah, it's gonna require a lot, and it's very interesting. Might get mad at us because you see it's doing a lot of analyzing. Nice. It's doing with Python code, I think. It is Python code. Here it is. It didn't get a 50% probability. You got to buy a lot of tickets. Oh, no, it did. It just did log scale. Really? Remake the graphic, but don't use a log scale. And the Y should go from 0 to 1. You can use the log scale. Cumulative probability. It never reaches it. That's a bad graphic. We gotta buy that many tickets? Run, buy enough tickets. There you go. Oh, you need to purchase 15 million tickets. He does spend $30 million. So the probability of winning it, that doesn't make sense though. So to win at least once, you'd have to spend $30 million. But it doesn't mean you will win. It's just then more likely you'll win at least once. I would double check the math on this. Because like Powerball gets pretty high, but then you might split it and you got taxes and all these different things. So lottery, you're not meant to make money off the lottery. Not meant to make money off the lottery. Just always remember that key fact. Lottery is a negative game where people lose money. If they're giving you money, wouldn't be a lottery. What should we do? What should we do? What concepts should we do? I might have to look at emails. What should we do? Who's here? And what do you want to cover? Let me save this. Any thoughts? We already did this at the start, I think. What are the 3 interpretations you need to know? You should know these. It's the only 3 written questions on the test. I've mentioned them a billion times. Here's a billion and one. Do you want to do cluster versus strata? Tyler, you want to review that? Slope, the intercept, the R squared. True. So cluster versus strata. Great job, Tommy, right there. Can we go over central limit theorem? Yeah, let's do that. I'll probably end a tiny bit before 4. So sampling methods, cluster versus strata. Sampling methods. Okay. So whenever you see a cluster, can we do a couple of questions finding a z-score? Try that. Might have enough time. Cluster sampling. What are key things you see when we cluster sample? Like when Brian says he goes out and buys boxes of donuts and tries all of them. Brian says we go out and we talk to students in classrooms and we talk to all the students in each classroom. Brian says we are going to go to a dormitory and talk to every student on a certain floor. What do you notice about clustering and why do we cluster? Cluster sampling is what? There we go. So you know, clusters have groups and you take a census on the groups. True. So you're going to take censuses. You're going to do a census on the group, and the groups are kind of randomly put together. That's the best sort of clusters. Compare this to stratified. stratified sampling goes the following way. We want to get the views of UT students on their education, so we take 10 students from each major. We want to understand how parking is, so we talk to 50 students from each class level of freshman, sophomore, junior, senior, and graduate. We want to understand what's going to happen in this next election, so we talk to 100 people from each state. What do you notice about stratified? Explain to me what you notice in those stratification examples. It doesn't, and Rob, good answer. It doesn't have to be the exact same amount. A lot of times you actually might take more because, well, frankly, with how the Electoral College works, you might do the same. But imagine there's a really small major at UT. You might only take a few students from that major because then you might undercover or overcover other majors. So stratifying identifies a difference and then samples in accordance to those differences. A lot of times, especially with my peers, you see like 50, 50, 50, 50. They do that for a lot of examples, or some of ours even do that. But if we wanted to get views of parking, do you think we would talk to more students or more faculty? Do you think if we want to get views on parking at UT and how parking is impacting people, is him? I don't know what that means. So if we want to, we would get the views of students more, and why? Why would we get the views of students more? We'd get the views of more students because there's more students. So if we stratify on parking opinions and we say there's faculty and students and staff too, I don't want to leave them out, but and also non-faculty staff students, there's more students than teachers. So we might talk to like 60% students, 30% faculty, and 10% staff. And we do it representatively of who parks. Does that make sense? And Preston said it perfectly. They represent more of the parking population. So you look at the way the population works, and then you say, let's take those percentages in our sample. It's based on the proportion in the population. Exactly. Does that make sense, Rob, right there? So if you say like, oh, there's 60% students who park and 30% faculty and 10% staff, then when you take your sample, you would say, let's talk to, 120 students and 60 faculty and 20 staff, because you do it by the percentages. But you don't talk to all the students. That'd be clustering, which would be a bad idea because that's not a random cluster. So stratified acknowledges a difference, and then your sample is taken in a way that respects that difference. You take the sample randomly. Random. So that is what stratification is right there. Stratification allows us to acknowledge a difference and then take the samples in accordance to the way the population looks. So if the population has some sort of characteristics, it's going to help us not undercover those characteristics by stratifying to acknowledge the differences and then take the samples in accordance. Central limit theorem, a little bit on central limit theorem here. So Tyler, I hope that helps out. My ears are popping. I'm congested. I want to eat some dinner. Okay, central limit theorem. The central limit theorem states two things. What two things does the central limit theorem state? Central limit theorem says two things. You're welcome, Tyler. Central limit theorem says two things. Central limit theorem says two things. The two things the central limit theorem says is that the distribution will get more what and more what. The central limit theorem states two things. That the distribution will get more what and more what. You can see it. The original distribution doesn't change. The distribution of means gets more normal and tighter as n increases. And what's interesting is we can actually see this in the equations. So if you go and look at the equations right here, here are the equations, and let's look. Where do these equations indicate that it gets tighter? Where do these equations indicate that it gets tighter? We have to think what measures tightness. Where do these equations indicate that the distributions get tighter? N. Because as n increases, what decreases? If n goes up, for either of these, standard deviation goes down. Standard deviation is a measure of spread for how spread out the distribution is. So for larger values of n, you're dividing by a bigger number, square root of that number in many respects, and thus your standard deviation decreases, it gets less spread out. As n increases, what happens to the mean of the distribution? As n increases, what happens to the mean of the distribution? As n increases, and we can look at the formula sheet for the answer, as n increases, what happens to the mean of the distribution? Does it go up? Does it go down? As n increases, it stays the same. It's not part of the equation. There's no n inside of here. So the mean of the distribution, as a rock would say, doesn't matter what n is. So the mean does not change based on the size of the sample we take. The standard deviation does. How about the shape of the distribution, which we just said earlier? As we get a larger sample size, the shape of the distribution will become more what? Here's a sample size of 2, small sample size. Here's a sample size of 5, might be large enough n. And Rav has said it right there, it becomes more normal. And so the central limit theorem states that it becomes more normal and tighter, and this goes into Noel's question. Well, that's why we can use z-scores. So here's a really good quick one. Let's see if you can solve it. You ready? So okay. What kind of data are we dealing with right here? Categorical or quantitative? What kind of data are we dealing with right here? Categorical or quantitative? What kind of data? We are dealing with cat or quant data. What kind of data? Categorical. Because the question of, do you eat your steak medium rare is a yes-no question. Does that make sense? So it's definitely categorical. So what is sigma for this question? I like playing games. What is sigma? Great job, Preston. What is sigma? Be careful. Be careful. What is sigma? Playing games with you. We're playing games with my heart. I can't sing. That's what a lot of people do on the test. They look for sigma. There is no sigma. Sigma deals with quantitative means. There is no sigma. So what do you have? Start identifying what you have in this question. So once again, you want to go to where you should be at and start identifying what you have. So what do you have? So what do you start telling me the notation? Candido, go in a little more detail. Rav, good job right there. Rav has, this is P equals 0.20, Q equals 0.80. Good. You are correct, Candido. Great job right there. That is N. Yep. Yeah, I just wanted you to, I knew you knew it. I knew you knew it. I just wanted you to say N. So, and then what else do we have? People get stuck on these next few parts. There's still more numbers to mark. So what else do you have? N is 200. What else do you have? X. Yep, number of successes. What do you do with X? What? I'm getting like 8-9 hours of sleep and I'm still tired. X over N equals P hat. 0.150. Is your body saying, I needed that sleep? I'm going to catch up on sleep and sleep some more. I'm going to bed at like 10 and getting up at like 7. That's 9 hours of sleep, right? Yeah, it's 9 hours. Of course, I'm like tossing and turning. So it's fun times. Okay. So mu P hat equals P equals 0.20. SDP hat equals P times Q over N square root. Is this odd? I mean, this question basically just has you solve out the whole thing. Why is X not on the formula sheet? It's just one of those more basic things. Evan's back. Tell a friend. We did some stuff here, Evan. It's at about the 1 hour mark. No, 50-minute mark. 50-minute mark. We did like a 13, 14-minute section on it. Check out the 13, 14-minute. Let me know if you have questions. Evan's back. Tell a friend. I like that. P times Q over N square root. There we go. You know I'm going to round that to? Around that to 0.03. So, oh yeah, we have class. I think I'm good enough to go in person. I think I'll be good enough in person tomorrow. I'm only like congested in one nostril as opposed to like I had both congested. No fever, no COVID. So, like, I will have in-person class tomorrow. Well, we will have class unless I'm really sick. But back to in-person. And I don't think I'm really contagious, but I always think you should try to look out for people, and that's hence why I've been more online. But still holding stuff. Like I'm well enough to teach, but wanting people to keep their distance from me a little bit. So unless I'm like outside, then I think it's a lot safer. So there we go. It's a nice day today. There's something to walking outside and enjoying the atmosphere, and it's nice. I already did standard deviation. P hat minus P over standard deviation. So P hat is 0.15. There we go. It's such a nice day. Like, enjoy some time. So this is not that odd. It's kind of low, not super low. And I could have taken the, like, there's the exact z-score. I rounded it. There's the exact z-score. Because you could have taken the 0.027. I just wanted to do it in my head. That was easy enough to do. There's the exact. So I'm confused at what step the x over n comes in. So that is the sample proportion. The sample proportion is what is observed in the sample. So if a question asks you what is the sample proportion is always x over n. Is x over n the same for y bar 2? Y bar will be for mean. So good question, Tyler, right there. There will be no x over n for y bar because y bar is a sample mean, and x over n only deals with proportions to find p hat. So y bar is the idea of the sample mean versus p hat. Like an x over n question is like 2 out of 10 people own bunnies. 0.2 is p hat. Y bar is Brian spent 100 on video games, Chelsea spent 200. Y bar is 150. So y bar is the average of a quantitative y variable, where p hat is the sample proportion found by the number of successes over the number of trials, like 30 people out of 200. So it's categorical. Like the people who conform, we call successes X, which means the people who conform. Any questions on this right here? It really boils down to notation. You'll hear me say that for the remainder of the semester. With that, I might end a tiny bit early. I have a 4 p.m. meeting, and I've gotten a lot of emails. I think everyone's getting sick like me. So we'll do a fun outro. I'm going to do my Star Wars outro. So if you haven't seen our fun outros here, stay tuned for a Stat Wars outro. Quick question, though. You're welcome, Garrett. Quick question. What was the large enough n if the shape was normal again? I remember it's 125 and 100. So it's 125 and 100, Elizabeth. So if it's normal to begin with, then, so here it is on the screen right here. If it's normal, like if the question states it's normal, then you don't need a large sample size. So I always review it this way. Do we pass the large enough n condition with a sample size of 2 here? Yes or no? So it wasn't that odd. TZ good. It was not odd because the z-score was within negative positive 2. Because z-scores outside of 2 are kind of odd. And so this is a large enough n. It's a large enough n because the original distribution is normal. So since the original distribution is normal, you only need a sample size of 1. So when you run the simulation rate, Preston said it, it's already normal. It's just going to, say it with me, Preston, since it's already normal, it only gets what when I do it, but it was already normal. So it's already normal. It's just the central limit theorem states it'll just get what normal. I think Preston's RC is like, well, it's already normal to begin with, and the central limit theorem states it will get tighter and more normal, but it's already normal, right? Does that make sense? Like, it was normal, and now it's more normal, but it was normal, so more normal means it's already normal because it was normal. Does that make sense? I think Preston kind of sees it right there. It's like, well, if it's normal, then the sample size wouldn't really matter because it's already normal. Because it's just going to get more normal, but it's already normal. I think we might do in-person office hours. My throat is not sore, which I'm noticing right now. My throat is not sore. So just, you guys love the Brian health updates. My throat's not sore. One nostril is clogged and feel a little hot, but not like sweaty hot. Just like probably the light's hot. Got the hot lights in here. Hot lights. Yeah, so I think I'm like 85% today. Like I've had days when I'm 25, 30 doesn't matter. If a test question is mean to you on that. The name in the chat. I swear people are just trying to. What Z-score makes an event odd from former president? Right there with the interesting spelling of the name. I don't even know sometimes. So a z-score that is odd is either 2 or 3. Now, why do I say either 2 or 3? 2 is kind of odd and 3 is very odd. Because like it's like, when is someone tall? Well, a guy being 6'3" is kind of tall. A guy who's 6'6" is very tall. A 6'3" guy has a z-score of 2, kind of tall. A 6'6" guy has a z-score of 3, very tall. So some statisticians go by the standard outside of -2, no worries. Outside of 2 and -2 is considered odd. And that's a lighter standard. Some statisticians go by 3, and some use the 1.96, or I might say 1.95996, because I'm obsessed with it. So we will have to use the 1.96 z-score, kind of, sort of. That's traditional 95% confidence interval z-score, but statisticians don't know it's 1.95996. I just like it. That's the extra decimals that you don't hear. But that's a very classic number in statistics. So the answer to your question is -2 and +2. Outside of that is kind of odd. -3 and +3 is very odd. Good news on the test, we usually throw you z-scores that are extreme or not extreme. Z-scores that are not weird are usually going to be things like 0, 1, 1.5, 0.8, -0.8, because that's just the other side. Z-scores that are going to be extreme and we consider odd, I never like going between that 2 and 3 range, because it's kind of like an iffy range. Like some people are like, yeah, that's weird. Some people are like, man, that's not weird. But Z-scores that are odd, we're usually going to throw you something like 3.5, 4.8, -5, -6, -50. If you get a -50 Z-score, that's insane. That's super duper below. Like the distribution's here and you're way off the curve. So we will usually give you something that's very intuitive if it's odd or not odd. And the not odds are usually closer to 1 or 0, -1 or 0, 2. The odds are going to be more something like 5, 8, 7, 10, -5, 8, 7, 10. I don't like when we give something like -2.1, because it's like, it's a little weird. Like, I don't know. We should make it very clear. It should be obvious. And then we can calculate probabilities. Okay. Here's our outro. Stat Wars time.
We've almost got these new intros ready. We're almost there. This has been going for like 20 hours. This ends now.